Project 2430, Remote ID Drone Detection, sponsored by L3 Harris, and this is our Design Day video. Hi, I'm Darius Carozzo. I'm Electrical and Computer Engineering, and I'm the team lead.
Hi, my name is Nicholas Coyne. I'm an electrical and computer engineering major, and I'm the procurement lead and the electrical lead.
Hello, my name is Jesus Saldana. I am in systems engineering, and I am the mechanical lead.
Hello, I'm Evan Martin. I'm in software engineering, and I'm the software algorithms lead.
Hello, my name is Connor Toole. I am studying software engineering, and I am the software architecture lead on this project.
For the project background, it is based on the Federal Aviation Administration, or FFA, new guidelines that have all commercial and consumer drones that are greater than 0.55 pounds to transmit specific information. This includes a serial number that is unique to the module and the drone, longitude, latitude, geometric altitude, and velocity of the drone, longitude, latitude, and geometric altitude of the takeoff location, as well as time mark for each data collection. Currently, most drones are not able to do this inherently, so they're relying on external attachments, known as the Remote ID module, to complete this functionality. To give a better idea of how the Remote ID module works in conjunction with the drone, as mentioned, it is an external attachment that the user can attach anywhere on the drone that they see fit and allows to not impede on their performance of flight. Once it is powered on by the user and put into flight, the Remote ID module will continually send out the required information to any applicable receiver at least once per second. Any receiver, which in this case would be mostly phones and applicable applications, will be able to pull it up and be able to see all the required information that is required of Remote ID transmissions. This ability is provided to any user or any person with these applications and not just the operator of the drone. So with that being said, our task as a team was to design and develop a low-cost software and hardware implementation for L3 Harris's own Remote ID module. So our process and plan to solve this problem was utilize off-the-shelf component that allows us to develop the software functionality as well as design a possible printable circuit board or PCB implementation for L3 Harris. In order to complete this functionality and meet the requirement, the team wanted to use few components as possible while also ensuring all functionality. So that being said, there were two main components of the system: the NRF52840 system on a chip and the GPO2 GPS module. The NRF52840 system on chip allows for easy Bluetooth 5 capability, allowing the team to send out the information via coded PHY, and the GPO2 is high accuracy GPS data collection that can easily interface the NRF52840. They communicate via UART and NMEA sentences to get all information necessary. Other than that, all of the components were for easy implementation of the rest of the requirements. The TP4056 charger is an external battery charger that allows us to interface with the 3.7 volt LiPo battery to both charge it and send out power to the system, as well as having LEDs that allow to interface with the user to tell them when the battery is charging versus when it's fully charged. All of their battery LEDs, such as the Bluetooth LED, the GPS, and the battery LED, all provide information that makes sure that Bluetooth is connected, the GPS is connected, and the battery is at a sufficient battery charge to provide power to the system for a long period of time. For the actual software, the team's goal was to make it as abstract as possible, taking certain electrical components and main components of the system and splitting them to their own classes and structs in order to simplify the process of calling functions and utilizing the information and passing it around. We have our main C file, which initializes the whole system, and then have our main loop, which allows to call the battery and control whether it has a sufficient charge, update LEDs for a whole system, read GPS information, parse the GPS information, get the serial number, and then call the Bluetooth. Breaking it off into our abstract, we have the battery as its own class, allowing to read and update the LED of the battery, the LEDs, which allows to go on and off of the LEDs, as well as the Bluetooth, allowing us to start the advertising packets and update the packets as necessary. We utilize key libraries such as Software Serial, Bluefruit, and TinyGPS Plus, allowing us to easily pull the GPS information and set up the Bluetooth transmissions. In order to develop the system, we need to utilize the same components but in their development kit format. This included our GPS module, our GPS antenna, our Nordic chip on the NRF52840 Adafruit Feather Express, which has its own onboard antenna, the LEDs attached to a breadboard, and the 3.7 volt LiPo battery. Having this developmental system designed, we're able to easily interface it with the software in order to design the system we need to meet L3 Harris's requirements. What the developmental design looked like in the PCB implementation was very similar, but utilizing only the basic chips from both the modules. As seen, the NR52840 system on chip is the only component we took from that, but employing different resistors, capacitors, inductors, we're able to verify the specific necessary needs we needed for the requirement and the functionality of our system. The GPS module on the left, the GPO2, is similar, just taking the chip and interfacing with antenna to make the system work as necessary. Ultimately, the other components would be the TP4056 charger, seen in the bottom left, which in this case would be soldered on for the design aspect of this PCB. And then finally, the USB-B port, which is important for and vital for flashing the software onto the chip. What this ultimately looked like on the PCB implementation would be a simplistic design, thin, only 6 layers, but containing all the necessary components for the functionality. Our key point was making it lightweight and thin so we would not run into a weight issue. Ultimately, what this design looks like in action is very simplistic to understand as mentioned. Below and the bottom are the LEDs. The blue LED represents that the Bluetooth is being transmitted. The flashy green LED transmits that the GPS is connected and collecting information, and the LED signifies the battery power is supplied to the system. Ultimately, as mentioned, we have the blue NRF board and the GPS module and the battery. However, what this looks like in testing is very simplistic as well. Here we have on the left the actual system being run on its own on the breadboard. On the right is the NRF Connect application collecting information as our team member walks further and further away. As seen, the strength of the RSSI signal is decreasing as he gets further and further away, but we see that every about 100 milliseconds to 200 milliseconds, another transmission is collected from the device. And from those transmissions, what matters most is the beacon UID message. Here is all the GPS information, the serial number, the time mark, all collected in this hexadecimal 25-bit message. Ultimately, this is what we were looking for and is what we need to transmit to meet the remote ID requirements. Now looking at the requirements that were set out by L3 Harris for our project, it can be seen that most of our requirements were met. The key one being message rate, where we're able to send out the transmission at least once per second, where in the last video we saw that it was between 100 to 300 milliseconds between transmissions, easily matching what we needed. The key one we did not meet was distance. While we were able to reach a maximum of 250 meters with connection, ultimately we kind of fell short to about 200 meters consistently. So while we are looking into ways to implement a stronger external antenna to make sure this meets it, we were not able to meet that requirement. However, all our collection rates, our actual information collected, our serial number, as well as information such as the time mark and our battery life, battery hold, all met the requirements of our system. So in summary, as a team, we were able to develop the key software design for GPS collection, parsing, and transmission via BLE protocol. We ensured packet collection was with the remote ID transmission formatting. We extended the range to about 200-250 meters. We developed a design that is battery operated and has low power consumption, as well as an RF PCB design that is ready for verification through manufacturing. While we were unable to reach the stage of testing PCB design, we believe that this is the next step in the project to create a fully functioning remote ID module ready for the market. Ultimately, that design, as mentioned, is ready to be manufactured and tested with the completed software. So in general, we want to say thank you to L3 Harris and now Joseph Ellis, our sponsor, Mike Majerick, our mentor, and any subject matter expert outside of the school that has been helpful for us developing this project. It's been a great learning experience, and we can't wait to tackle further problems.